Florida averages roughly 55 inches of rain a year. It is not supposed to burn. Yet, in the first 3 months of 2026, the state logged more than 1,500 wildfires, the worst conditions the region has seen in a quarter-century. The economic toll follows the same trajectory. A brutal January freeze destroyed citrus and vegetable crops already stressed by months of drought. That compounding damage pushed agricultural losses past the $3 billion mark. The crisis expands north across the entire region. Alabama is 100% covered in drought, every single square mile of it. Vital water reserves, reservoirs, and canals across the southeast are drawing down in real time. Normally, exiting La Niña shifts atmospheric patterns, delivering massive moisture from the Pacific directly to the southeastern United States. But a stubborn Bermuda High, a massive high-pressure barrier parked over the Atlantic, deflects that rainfall away before it reaches the coast. While this atmospheric block is a seasonal weather event, it provides a regional snapshot of a broader failure mode. The same physics starving the southeast of rain are now appearing at the scale of a permanent hemispheric breakdown. This globe models the Atlantic Meridional Overturning Circulation, or AMOC. It is a colossal deep ocean conveyor belt. Every second, it transports roughly 20 million cubic meters of warm tropical water northward, while pulling cold water south along the ocean floor. The engine powering this loop sits near Greenland. Here, salty water becomes extremely cold and dense. It gets heavy enough to sink, and as that water plunges downward, it pulls the rest of the global circulation forward. Record-breaking seasons of Greenland ice melt are now pouring immense volumes of fresh water directly into the North Atlantic. Because fresh water is lighter than salt water, it floats on the surface, capping the dense water and preventing it from sinking. Disrupting this northern engine breaks the delivery system for the entire hemisphere's thermal energy and moisture. A study published by Portman and colleagues on April 14th put a number on this decline. Their headline finding projects a 50% weakening of the AMOC by the end of this century. Most long-range climate projections use CMIP6 models, simulations that have historically carried wide margins of uncertainty and underrepresented the speed of ocean changes. Portman's team used a technique called ridge regression, applied directly to real-world sea surface temperatures. Instead of asking a model what might happen, they constrained the projection with actual measurements. The uncertainty window narrows dramatically and tightens into a single trajectory. The real ocean is tracking toward the worst-case scenario of the older models. Severe AMOC decline is the trajectory we are currently on. This map highlights the AMOC's role in positioning the Intertropical Convergence Zone, or ITCZ, the equatorial band dictating where most tropical rainfall is generated. As the Atlantic circulation slowing, the ITCZ rainbelt shifts downward, taking essential moisture away from the northern hemisphere. Data from these ice cores shows this happened 12,900 years ago, during the Younger Dryas. A massive influx of meltwater shut down the AMOC and rewrote global wet and dry zones for a millennium. The physics of the current southeast U.S. drought, the failure of the atmosphere to deliver moisture, is exactly what broken moisture transport looks like at a regional scale. The current decline is already significant. The AMOC is at its weakest point in 1,600 years. Escalating predictions from researchers now suggest a full system collapse could occur in the middle of this century, with some estimates pointing to 2057. The weather-driven drought in the southeast will eventually break. But the dying ocean current that governs global rainfall is a permanent problem for the families living through water shortages today.